Hello everyone, Human Hard Drive here. This video is a behind the scenes for the Acrobatic Lumina Shield demo I did a little while back. So if you haven't seen the video, check it out. Pretty cool what I did, if I do say so myself. Essentially what I did was I took audio input from a music player and ran it through the Arduino and turned it into a VU meter. So what a VU meter does is it takes an audio input and then displays the levels of various frequency bands across the display, and that's what it did. So you got the bass here and the higher frequencies as you moved farther right. So it fit onto an 8x5 display. Now, when I started doing this, because this is an 8x5 display, it's a little small for my taste. It makes it hard to put like text on here. I'd consider doing like Pong, turning it this way, seeing if I can get Tetris to fit on it. And none of that really worked. I'd gotten a couple suggestions from some friends to create like a wave thing going across it, but played with that. That didn't really... I wanted to show just what you could do with this. And like the text and the Tetris games and all that, I wanted to show that A, you can write to any pixel here, which you could do with those games, but secondly, or B, or whichever I said, is that these are RGB LEDs. You can get an incredible range of color from every single one of these pixels, and that's what I wanted to do. So the VU meter idea I got from a video I was sent a little while ago about the LOL shield, the Lotso LED shield, which I don't have on my desk at the moment, but there's probably a picture of it on screen right now. And what that person did was they turned the Lotso LED shield into a VU meter. So that's what I wanted to do, but I wanted to add color to it. So if you watch the demo, you can see that as it goes higher in the y-axis, it becomes redder, and as it moves this way, it becomes greener, and there's this sweeping, like, randomized color that moves across it. So it added a lot of depth to that project. So that's where the idea came from. Now, to do this, all I did was I took an 1/8" MP3 cord and one of these jacks here, put it onto a breadboard, and then plugged it into the Arduino. Now, I had to break some of the pins off to do this. I broke off the A5 pin down here to get a jumper into the A5 pin, which was the analog read pin. And I broke off the AREF pin as well to get a jumper to feed the analog a reference voltage. Ended up not using that. There we go, proper English. Ended up not using that. I used an internal reference voltage, as you'll see in the code. And I lopped off some extra pins because I've got an older version of the Arduino, so I lopped off the IORF pins and the I2 pins that are up here on the Rev 3 boards. Mated that together like this, and that's what you saw. Now, to play the music, I get out my phone here, because that's what I used to play it. I've got this app on my phone because I like to make or at least play with the idea of making music in my spare time. It's this great app called Caustic, which one of the demo songs that's on here, that's what I played. And the great thing about it is, because you can use it to make music, I had to do a lot of testing to make sure that everything looked good on this, to make sure that the frequency spectrums I felt were equally represented. So I could play with the equalizer to make sure everything was balanced out. I could play with various synthesizers within the song to make sure that everything played out just right. So that's what my phone helped do. It played the music, and I was able to tweak with the bands on the phone as well to make sure that everything looked good. But that's really it hardware-wise. Let's go ahead and take a look at the code that was used to make this thing work. Alright, so here's the code I was working with, and I'll post this in my GitHub, which is linked in the description. So, to start with, a lot of this code was borrowed from the LOL version of this project. You can find this project on Instructables. I'll link to that in the description as well. So a lot of this code is from that, and I just had to tear it apart and rewrite it for my needs. Now, the way the code works is based on an FFT algorithm. If you don't know what an FFT is, it's a fast Fourier transform, which is a fancy mathematical function which takes an analog input and essentially tells me what the amplitude of various frequencies are in that input. So it's a really useful algorithm, and it's great that someone's written it that works on the Arduino, and it is actually pretty fast and efficient. So that's how that works. And I had to add the NeoPixel library, which allows you to work with the RGB LEDs, or the addressable ones. I didn't actually end up using the analog or the VREF pin. I just used an internal 1.1 volt reference, because using a 5 volt reference is a little too high for analog input coming off of a phone. And again, this was all just testing I did to make sure that everything looked good. Also drastically turned down the brightness because it would absolutely destroy the video, because again, went through a lot of testing to make sure that this looked good on camera. So a lot of this is, it pulls in a bunch of samples, then it does a fast Fourier transform. I pull it out, I convert, or the code converts it to a real number, then I split it into 8 bands for the 8 pixels, so it's 8 long by 5 up, and then I actually write it to the screen. Now, set pixel color, XY, strip color. So I did a little randomizing here where I added, so it added the millisecond timer to the RGB scale, so it created a color shift across the entire screen. So that was that. That's how that works. So if you watch the video, you should see color shift across the screen, or shift across the display. That's what the millis is doing. The higher, let's see here, the higher it went, I think the redder it became. Yeah, the higher it goes, the redder it became, and the less blue it became, and the farther it moved across the screen, the more green it became. So that's how I created all the pretty colors you saw. Now, one of the tricks was that the RGB Shield uses sequential addressing, which means it goes up a column, then down another column, up a column, then down another column, whereas the LOL Shield uses an XY coordinate system. So part of what I had to do was take an XY and tell me which LED in the string I had to write to. That was a bit of a pain, but that had to be figured out. And the other thing was that I mentioned I got a lot of display in the base, probably because of sampling issues, probably because of the fact that it uses a sine table to interpolate what I'm putting in, which isn't the best because you're dealing with limited resolution. Another thing is trying to run a fast Fourier transform on this isn't the best idea, but it works. So I got a lot of things in the baseband, so I applied a logarithmic shifting so that the lower the frequencies, the less multiplier it had, so it appeared smaller, but the higher the frequencies, it grew a little more, so I tried to balance everything out. And that's pretty much everything that went into this. It was, like I said, a lot of taking the LOL Shield VU code and rewriting everything for the Lumina Shield. But yeah, I think it worked out pretty well. I certainly liked how it looked given the input. Like I said, this is available on my GitHub if you want to check it out. Shield's really cool. Play with that. Thanks for watching.